Hi, this is Miss Logan. Today I'll be discussing acceleration, the kinematic equations, and free fall. All of this will be for one dimension. So to get started, what is acceleration? So acceleration is the change in velocity over the change in time. We can write this out a little more clearly when we actually write out what the change is. So that's the final velocity minus the initial velocity over the final time minus the initial time. So just to kind of think about this, if I am starting out with an initial velocity of, let's say, 3 meters per second, and I am going to slow down to 0 meters per second, my time is always going to be positive. So this means that my acceleration will be negative. Okay, and this is something really important to remember. Now, some teachers use decelerate as the same words as negative acceleration. I like to use negative acceleration or positive acceleration. I really don't like using decelerate. I think it's sometimes confusing. All right, so looking at the velocity versus time graph is kind of similar to how we look at our position versus time graph. Okay, so as a reminder, slope is my change in y over my change in x. And if we look at our two sides, on my y, I have the change in v over the change in t. Okay, that is my equation for acceleration, which I showed on a previous slide. Okay, so how am I going to figure out the instantaneous acceleration or the average? Well, to figure out the average acceleration, I'm going to use the slope between two different times. That's the exact same thing as this equation right here. If I'm looking for the instantaneous acceleration, I'm going to be using my tangent line. Okay, so let's start getting into our equations that will help make our list of our kinematic equations. So if our acceleration is constant and my velocity is changing, then we're going to use this equation. So this is my final velocity equals my initial velocity plus acceleration times time. Okay, so this equation, and like many other equations, are just our acceleration equation written out in a different way. Okay, our next equation we'll use is our average velocity equation. So that's our velocity average equals 1/2 times velocity initial plus velocity final. And you can see that on this equation right here, or on this graph right here, that we're taking the difference between these two different points. All right, so going back to position versus time graphs, it's important to remember that this curve means that we have acceleration, okay? However, if we saw a straight line, that means that we would have a constant velocity. Okay, we'll explore this a little bit more, but these are important relationships that we need to know for further on in this unit. All right, so let's dive in talking about our kinematic equations. So there's 5 total, and actually 3 of these we've already talked about. Okay, so I'm going to break this up into a couple different columns. And first, we're going to talk about the variables that we have and what we don't have. Okay, this is going to help us kind of figure out what equation we need to use. So first one, we have delta x equals v over t. So this is just our velocity equation written in a different way. So the variables we have in this one, we're going to have x, v, and t. We do not have acceleration or distance. All right, so our next one, this is the average. So this little line up top means average. Okay, you may have seen that before in math class. Okay, so this is our average velocity equation. In this one, we have average velocity, velocity initial, and velocity final. Okay, what we don't have, we do not have acceleration, we do not have distance, and we do not have time. Okay, our next one. So these equations are dealing with our average acceleration. So our first equation, we have VF, V0, A, and T. What don't we have? Well, we don't have distance in this equation. So if we were looking for distance, This is not the equation that we would start off with. All right, next one, we have delta x. So delta x is the change in my distance, and this equation can be written out different ways, and we'll talk about that in class a little bit more. So in this equation, I have delta x, I have v0, I have t, and I have a. What don't I have? V final. So that's the equation we do not need to use if we're looking for V final. And our last one, I have VF, V0, A, and delta X. What don't I have is T. Now you may notice that there's an equation we're quote-unquote kind of missing, and that's our acceleration equation. But like it was shown on our equation to memorize sheet, that's just something we have to have memorized, so we could even add this to the bottom. So A equals VF minus VI over T, okay? So in this situation, I have, make some room, VF, acceleration, VI, and T. What I don't have is delta X, okay? Just a note that these are the equations that are given to you on your AP test. All right, so let's talk about how we'd set up one of these problems. So a car is traveling at 10 meters per second and accelerates to 16 meters per second in a total of 12 seconds. What is the total distance the car is traveling? So let's write down the things that we know. So our initial velocity is 10 meters per second, and our final velocity is 16 meters per second over a time of 12 seconds, okay? We're looking for delta X, and we should probably also figure out our acceleration. Let's start off by figuring out our acceleration. So we're going to have acceleration equals VF minus VI over T. Like I said, this should be a memorized equation. So we're going to have 16 meters per second minus 10 meters per second over 12. So I'm going to get 0.5 meters per second squared. And that's for my acceleration. I'm looking for distance though, so I am not done. Now take a minute to go back to our kinematic equations that you should have written down. At this point, I have velocity initial, velocity final, time, and I have acceleration. So there's only one that I can use. So that's VF squared equals VI squared plus 2A delta X. Okay, so my first step is that I need to rearrange this equation. So let's take a minute to do that. Delta X. Okay, from here I can plug in my numbers. So I'm going to have 16 squared minus 10 squared over 2 times 0.5 equals delta X. So I'm going to get a distance, so I'm writing over of 156 meters. All right, our last topic to discuss is freely falling objects, okay? So when I'm in free fall, nothing else is acting on an object except for gravity, okay? And G is always going to be 9.81 meters per second squared. This table is just showing you how G can be a little bit different when we're throughout the world. However, it always averages to 9.81. So an object falling in the air is subject to air resistance, and that is when it's not free falling. So when I have just a paper falling, like right here, we do have air resistance. But if we're crumpling it up, there's not as much air resistance or none. So a freely falling object is accelerating, okay? So its velocity is changing as it's falling. So this is just showing a ball that is being dropped. Our initial velocity is 0 right here. And as time increases, you'll notice my velocity is not changing linearly. It is changing with our 9.81 meters per second squared. Okay, so over time, my velocity is increasing pretty rapidly. By 4 seconds, I'm already going 40 meters per second. So this graph is showing us a projectile, and this is going to help us start to think about our 2D unit, which we'll get to next week. Okay, so my object, when it comes up to this point right here, my velocity is 0. So anytime we have the top of a projectile, and this is whether I'm throwing it up or not, my velocity at the top is 0. Okay, this is going to be really important. Another thing to note is my acceleration in this situation is always 9.8 meters per second squared. Okay, so this is just something to think about. We're not going to be doing 2D right now. We might be doing some problems where I'm throwing something up and then it's falling back down. And in these situations at the top, my velocity is always 0. Another thing you'll notice on this graph, which is good to point out, is that as my object comes up and comes back down, it is always the same velocity at different points. Okay, so this is just a trick to help you out. All right, so please complete the Google form and press done on Google Classroom.